IEEE CEDA Distinguished Lecture Program. This program aims to promote the field of electronic design automation to scientific community and the public at large. During the pandemic, and when we walk out and from the pandemic, we arranged the virtual DL lectures. And today we are very honored to have Professor Yiyu Shi be with us. Dr. Yiyu Shi is currently a professor in the Department of Computer Science and Engineering at the University of Notre Dame. He is also the site director of NSF IUCRC Alternative and Sustainable Intelligent Computing, and the director of the Sustainable Computing Lab. Professor Shi graduated from Tsinghua University with a bachelor degree in electronic engineering, and then he received the master and the PhD degree in electrical engineering from UCLA. His current research interests focus on hardware intelligence and biomedical applications. He received many awards for his excellence in research. The examples include the Best Paper Awards in top journals and conferences, like 2021 IEEE TCAT Donald Pedersen Best Paper Award. He also the recipient of a Facebook Research Award, IBM Invention Achievement Award, NSF Korea Award, and many others. I also wanted to thank Dr. Shi for his extensive service to IEEE and ACM. So Yiyu, now the floor is yours. Thank you.
Thank you, Helen, for the kind introduction, and good morning or good afternoon, good evening, wherever you are. It's my great pleasure to be able to be part of the CEDA Distinguished Lecture Program and to give a presentation on some of our most recent research on AI for mobile and implantable devices. So just to start, right, I think everyone is probably more or less familiar with the mobile and implantable healthcare. Just to give some examples. So for the mobile healthcare, people typically would rely on mobile devices like smartphones to provide some health information. For example, the skin cancer detection, the cardiac monitoring, the RPPG, where you can take a video of your face and then it'll give you your like blood pressure, heart rate. So these are all like based on mobile devices. There are also another category which are we call implantable devices, where we actually implant these devices in the body in order to provide better health care. Examples including what I listed here, the implantable cardiac monitor, which you kind of insert into the cardiac area in order to provide close monitoring of the heart rhythm. There's an implantable cardioverter defibrillator. There is a cochlear, basically we would put in your ear to help with the hearing. There's a deep brain stimulation, which helps with the brain, with the central nerve system. Right, so there are lots of actually different devices that we actually use to provide the help. Now, actually, with the prevalence of AI in the past few years, there's been a trend to try to make these mobile or implantable devices smart, right? Some of the examples I've listed here, including the smart skin disease diagnosis, where I think there are quite a few commercial apps today where you can take a photo of your suspicious area of skin, and it will automatically tell you based on AI is that something that it should be of concern, that you should go and see a doctor, or something that's okay, right? You don't have to worry about. There is also a smart cochlear implant where you put in your ear and it will automatically adjust itself based on the surrounding environment, right? So these are just examples. But in order to make these, smart, or I call it on-device AI for these kind of applications, is basically you would have to run the AI algorithm locally on these devices, and that because of the latency constraint, where sometimes you can't just really wait for a long time for it to for the treatment to come or for the prediction to come. There's a power constraint you have to consider. There is a security considerations where, you know, if you send things over to the cloud, then there is basically additional risk that your data could be subject to attack. And of course, there's the privacy issues, right? These health data, they are quite sensitive. And you know, due to various reasons, we actually we've seen that there are still a lot of applications today that are not really what we call the modernized with AI. Examples including, for example, the ICM, the cardiac monitor, where you know put in the heart. Right, they are more or less still like evidence based. And these and therefore there is an ICD for a similar, you know, cardiac device which would deliver a shock if some life-threatening event has been detected. And for those kind of cases where the people still rely on the rule-based anomaly detection. We look at some clinical rules and see, hey, if the monitored signals would satisfy some of the conditions that would lead to some potential issues, right? So these kind of designs, they were at least 20 years old, if not more, right? So why don't we just kind of introduce AI or machine learning to these problems, right? Or to these kind of designs? So there are basically two big challenges as we have identified. The first challenge, I think everyone here in the community is probably very well familiar with, is the limited hardware resource, right? And there are limits both in terms of the total memory footprint, the flash memory, you know, those kind of memory constraint, and the power constraint, because again, we have to put them on the edge, so on these devices. So we do have to consider these potential constraints. And we did a study back about 5 years ago. So we look at all the leading neural networks in terms of their performance, right? The x-axis in this figure is the top 5 error. So basically towards right, the model gets a higher performance, lower error. But the y-axis are the basically the number of operations needed for these models in order to handle a single image. So if you look at the y-axis in the log scale, that basically means in order to reduce the top 5 error, you are essentially seeing an exponential increase in terms of the number of operations needed. And at the same time, if you look at the hardware platform that would support these neural networks for on-device AI, we can see that over this 5 or 6 years of period, basically, doesn't matter if we're looking at FPGA, we're looking at the ASIC, we're looking at a GPU, or these different color curves showing basically it's showing different platforms, GPU, ASIC, and FPGA. But it doesn't matter. Just basically, you can see that it's increasing a little bit in terms of performance density, like per unit time, per unit area, how many operations can be handled. But apparently, it's not in the log scale. Sorry, in the exponential scale that would match the increase in the neural network models. And a similar trend that we have observed, that this figure again, but it's also for these kind of different neural networks. But the y-axis here is the number of parameters, basically the size or the footprint of the model. And also, if you look at the energy efficiency now in terms of, hey, let's say we want to move these parameters around, right, between the memory and the data path. So look at the trend here for DRAM and SRAM, you know, the on-chip, off-chip. But look at the trend here. It's also increasing, like with the unit energy, like nanojoule, how many bits we can move. It's increasing, but again, not at the same pace as we would see in the neural network size increase. Okay, so that problem, that gap is actually getting bigger. So what we, on the other hand, if you look at these kind of implantable or mobile devices. So I have two tables here. The top one is showing some of the example applications for the implantable healthcare. The bottom table is showing the some of the mobile devices people typically use in the setting of mobile healthcare, right? I'm listing their potential physical size, the supply voltage, the current, and how long they need to last. And especially for, for implantable devices, once they're implanted, you can't expect to take them out, right? And then recharge. So if they're there, they're just going to be there for a long, long time. So especially, for example, the ICD, right? You put it in and it's going to be there for 10 to 15 years. And under a normal operation condition, if there's no events happening, it's just providing the surveillance functionality, we would expect the current to be around 10 microamp on average, right? In a very small area. So this, again, the real time, we need to detect things in real time, right? If anything happens, we need to provide a detection over a long period of time. We're talking about years, 10 or 15 years, for example. And any suspicious events needs to be stored in the on-chip memory, right? Once you in-device memory, basically. And you consider, again, we have those limited battery, we have limited memory, we have limited computing power, right? So how do we make this happen? So that's one of the biggest problem why we are going slowly when we are transitioning from the conventional, simple, like rule or evidence-based method into the AI-based method. It's just, it's very, very complicated. And now the second challenge actually we identified in this area is really the AI. If you want to use AI, like on-device AI towards this healthcare, there is a disparity issue that we have to be aware, right? And there are two different disparate kind of things we actually observed. One is that these models can provide like a biased decision or prediction based on some features that are irrelevant. So in the comics here, I'm showing that, hey, this is not about healthcare. It's about a long kind of approval. But the AI model decides that the loan needs to be denied based on the hair, the style of the hair, right? So that's just one example. The second situation is where, yes, I can have an AI model that works very well for a big population of patients, but there may be a few, and there's always actually a few outliers that are not taken care by the AI model very well. And if you're familiar with the this kind of AI performance, you're probably aware that there is no guarantee at all in the worst case performance. This is not like a rule-based or evidence-based where we can always control, hey, well, this is the worst case. I can guarantee you, it won't be too far off. But you never know, right? What's going to be the worst case for an AI model. So that's the other concern people would have. And just to give you an example that, again, what we have studied for, this is AI-based dermatology. Those basically we call the smart skin care apps. And there are, again, lots of these apps today in app stores, where you can take an image, a picture of your skin, and then it'll tell you, hey, what kind of disease it is, right? And behind the scene, there is a neural network model. I think people are, very familiar. I can just train the model with these skin images and then train it to correctly predict what kind of disease it is, right? So that's the easy part. But the problem is, we look at the prediction. And for example, we look at the Fitzpatrick data set, which is a skin disease data set that has different skin colors from type 1 to type 6, going from light skin to black skin, right? From light to black. So we look at the accuracy of the classification of skin disease per skin color, right? Do we see similar skin colors or like similar accuracy across all skin colors, or do we see a bias here? And the results we identified is pretty interesting. So actually the learned models show discrimination towards skin colors, which we call the sensitive attribute, the skin color here. And what is more interesting is initially we thought that, hey, maybe the dark colored skin would lead to a lower accuracy. Number one, because it has fewer data in the data set. And number two, because the skin color, the dark skin color usually provide a lower contrast with the skin disease, which is usually also in the dark color, right? So the problem is more difficult. But on the other hand, we see that actually the dark skin color actually leads to the highest accuracy. It's much higher than the brown, which is the lowest in terms of accuracy. So usually these kind of costs are either you have the unbalanced data set, you have the attribute induced challenge where different skin color possess different kind of level of difficulty in the classification, or somehow the machine learning model during this learning process has accidentally taken in some sensitive attribute as the features, which are not really the features. But anyway, these are the we have not identified the exact cause of this problem yet. Apparently, it's not due to the unbalanced data. It's not due to the attribute-induced challenge, but somehow it is a problem. And it's also being acknowledged by a lot of media. There are reports in the literature showing that there's actually this kind of bias even in commercial apps. So another example I can give you is, let's say I mentioned that for the ICD, which you implant in order to kind of detect a life-threatening ventricular arrhythmias, VA. And VA basically includes two different types of events. We call the ventricular tachycardia, VT, and ventricular fibrillation, VF. The VT and the VF, they are just basically, you can think of it as anomaly in the ECG signal, right? Once we detect that, it's very, very dangerous and could potentially lead to sudden cardiac death. You probably, if you're a fan of soccer, you're probably aware of the very well-known event of Christian Eriksen, who was a player of Brentford in England Premier League, right? He actually suffered from this event during a game, and actually I think it's the goalkeeper actually provided the assistance on the scene. Very timely help, and then eventually he received implant of the ICD, and that actually made the ICD very, very famous, at least for that time of period. And he was able to go back to play after the implant of the ICD. Right, so ICD basically it's a very small device. It's battery powered. It would deliver the defibrillation. It's basically a high voltage shock to patients whenever a VA is detected. Okay, so that's the main idea. And but we can just basically use AI, right? We can train a machine learning model to detect these kind of events. So we can just train them to, for example, use the CNN to recognize a given ECG period, like episode. Is it VT or is it VF, right? So that's conceptually it's pretty easy, but we tried it, and the biggest problem here, as we identify, is also this the disparity. Because across different patients, there is a strong variance in terms of their morphological characteristics. So here on the left, I'm showing the ECG, the IEC, the intracardiac ECG signal from 3 different patients. And as you can see that it's quite different, right? Visually, they're quite different. And if you just apply this same machine learning, a pre-trained model onto these different patients on the data that we have collected, the x-axis here, for the figure on the right, it's the patient ID, the different patients. The y-axis is basically the accuracy, like how well we can detect these events, the VF event, for example, right? So you can see that there's a huge difference. For patient 205, we can get to 334, we can get almost 100% of accuracy. And for patient 335, we're only looking at something that's below 10%. And remember, this is about life and death, right? If this event happened, if you cannot detect it, the patient will probably just die. So how to solve the problem, right? How do we make it fair for all the patients? So that's why we actually started our research along this line about 7 years ago. We have 2 goals, in the big goals in general. The first goal is to better the design for the common good. So basically, we want to improve the performance for the entire population, right? For the common good. And we do basically our research is through the hardware and neural architecture co-design. And another goal that's equally important, especially for this healthcare situation, is leave no one behind. So, and for that, we had a few approaches today. I'm going to briefly introduce two of them. One would be the meta learning for personalization. The other one is the pruning for fairness. So let me start with the our first work, right? So yeah, we know we want to put those kind of neural networks on these kind of implantable or mobile devices, but the biggest question we always have would be what kind of neural architecture we want to put in, right? So in the early days, we usually kind of do a manual design. The famous ones include ASICNAS, the VGGNet, ResNet, you know, probably there are quite a few. They are being manually designed for each application, which would require lots of domain knowledge, which would require a lot of trial and error, and that's not very scalable. And because of that, people actually moved into the neural architecture search, the NAS, where you use a controller, kind of RNN-based controller to learn how to generate a better neural architecture, right? That's the basic user machine learning model to generate the best neural architecture. And this worked very well for like cloud computing, where you have enough computing power. But here we are talking about hardware resource limited situation, right? You have limited hardware power, you have limited memory, you have real-time requirements. So the search process in the conventional NAS doesn't consider hardware at all. So once you have whatever's being obtained, if you put it on the hardware, if it doesn't work, it doesn't work. It failed, right? There's nothing you can do. And in order to address the problem, then people came up with the idea of hardware-aware NAS, where you use a controller, you sample with the probability, you know, and then you not only evaluate that potential neural architecture in terms of accuracy, you also evaluate on the target hardware platform for efficiency. And to update the controller, you would use both the accuracy and the efficiency. And as a result, you would get a neural network architecture that works very well on your target hardware. But would that work for our particular problem? It doesn't really, because in our case, we also have the freedom to choose the hardware, right? So we don't even know what's the target hardware. We have that's something we can design. And because of that, we realized about, again, I think during 2017, 2018, that there was actually a missing link between the neural architecture kind of design space and the hardware design space, right? People typically consider these two kind of design spaces as disjoint. They are not connected. So we are thinking perhaps we can bridge these two together to find the best design for different applications. So, and that actually leads to our framework of a code we call the neural architecture and the hardware co-design. So compare with the hardware awareness that were before us, the concept of doing this co-design is that towards the end, you're going to get a pair. So the RNN controller not only just generates the architecture for the neural network, it also generates the design parameters for the hardware design. So we sample at the same time in both domains. So the RNN, this controller, is learned to generate the best pair of design in both domains at the same time. Okay, so that's the main idea. Eventually, towards the end, you're going to get both the architecture of the neural network and the design of the hardware that supports this on-device AI. Right. So, and also an advantage of this approach is that if you have this hardware exploration, right, the hardware kind of performance evaluation in terms of latency, in terms of power, it doesn't really require accuracy. You don't need the actual values of the weights to look at the latency, for example, right? The latency is going to be the same, whatever the numbers of the values of the weights are. So you can very quickly evaluate the latency. And if the latency is above your threshold, if it's over the timing spec, you can just truncate the training to stop. You don't have to train anymore, because whatever the accuracy, it doesn't matter. It won't fit. So this will actually speed up this design process, even though it looks like more complicated than the one on the left, like the hardware awareness. By doing the simultaneous exploration, you can actually get a speed up. So this is kind of like the timeline. There was basically in the first stage where there were like human invented neural architectures, and then the second stage we have the pure NAS. In the third stage, there are like different hardware aware NAS, and somewhere in late 2018, we actually published the first co-design framework at DAC 2019. And then there were lots of ongoing work, after this one that also does the co-exploration. So that's just kind of like the high-level idea or concept. But really, if you look down into the actual design, right? We're talking about what? We're talking about on-chip AI for like, especially for implantable devices. Now, in those kind of devices, because of that, you have very, very stringent requirement in terms of power, in terms of area, in terms of performance. So ASIC is the choice. Even for today's like rule-based or evidence-based designs, they are based on ASICs, right? So we do have to look at ASIC. We can't look at FPGA. We can't look at GPU. It has to be ASIC. But the problem with the ASIC is that the design space is huge, right? You can think about you basically you can customize everything. The data flow, you can do different kind of data flow. There is a different resource allocation, like how much do you want to put into your processing element, how much power and area you want to put into your memory. There's a different topology connecting the different processing elements in an ASIC. There are different communication schemes. So basically, it's just a very large design space, right? And how do we really do the co-design if everything can be customized? So we actually took one step back and say, hey, maybe yes, it's very, very complicated. So maybe let's reduce the complexity a little bit. Let's don't challenge ourselves too much. So instead of going with the everything being customized, we look at the published papers at that time in leading design conference like ISCC, JCC. We look at the most successful designs in terms of like their data flow, and then basically we would extract these designs as we call the templates. Okay, so once we have the templates, then the question would just become, how do you select which template to use? So the ones obviously are, for example, the DLA, there is CDNL, there is Iris, there is right, there's different kind of the template that we extract. And our problem then becomes, which template do you want to use for the problem? And then within that template, there are a few design parameters that you can customize, like the bandwidth, and there is like the memory, right? So what would be these parameters? So this would actually allow us to parameterize the design space of the ASIC and create a template pool. Okay. The next question we actually identified is that usually these ASIC designs are not just for a very simple task. They would at least be there for a couple of tasks. So what we identified also is that, so here I'm showing two example networks. One is the ResNet 50, one is the UNet. The ResNet 50 is good for classification. The UNet is typically used in the medical and biomedical image for segmentation. So they are different in terms of the image resolution. They are different in terms of the number of channels we have, right? Accordingly, in terms of the utilization, you'll find out that for ResNet 50, it would fully utilize the DLA data, the wait stationary data flow, but not the output stationary data flow. On the other hand, if it's a UNet, because of the high resolution and the shallow channel, you'll find that it's better on the output stationary data flow, but not on the wait stationary, right? So different tasks or different networks might use different kind of data flow and accordingly different templates. Right, they would lead to different kind of energy delay product as shown in the left. So accordingly, our problem would be, let's say we have multiple learning tasks, right? And we have a pool of ASIC templates. We have a constraint in terms of latency, in terms of power, in terms of area. Now we want to determine what's the best neural architecture for each task, the best ASIC design from the pool, the best resource allocation to that particular template, the best mapping and scheduling of our tasks onto the target hardware. So basically, we want to decide in both design spaces what are the best design. All right, so that's the main idea, and just kind of stay at a high level again, because we only have about 45-50 minutes. I would want to try to stay at a high level and just convey the main idea of our work. And if you are interested in any of these works that I discussed today, at the bottom of the slide, there is a paper that actually provides all the details that you can look at after the lecture today. But just kind of like on a high level idea, the framework that we develop is called ASICNAS. It has three components. The first component is a controller that samples the hyperparameters, both for the neural architecture and also for the ASIC, like which template to use, like what are the memory, how much resource we need to allocate for the memory, how much resource we allocate for the processing elements. And then we have two kind of processes. One is the architecture exploration. One is the accelerator exploration. The architecture exploration gets sent over to the evaluator that would evaluate, hey, for my sampled architecture, neural architecture, what's the accuracy? And when I put that on the hardware, on the sampled hardware, I have an ASIC cost model. It's the Maestro model that we used, initially developed by Georgia Tech. We use that basically to quickly evaluate what's the accuracy, what's the latency, what's the energy, right? And so that will, together, they will form a reward and penalty to update the controller. And in addition, we sometimes also only turn on the switch for the accelerator that used a few iterations just to kind of train better in terms of the hardware, because the hardware design space is more difficult. So we sometimes allow only to turn on the switch for the accelerator exploration, and that only goes to the cost model and the mapping and scheduling in the evaluator to evaluate the hardware performance. So together, this whole framework at the end of the training of this controller, it will generate solutions with the highest accuracy and the guaranteed that can guarantee to meet the hardware specs. So let me show you some of the results on the that we tested initially in the paper. So we tested on two workloads. One is the nuclei and one is the CFAR. So one is for segmentation, one is for classification. So I would not go into these numbers into too much detail, but basically we compared with three different approaches. One would be, hey, let's first search for the best neural architecture, and then we design the ASIC, right? The problem for that is that you can get the highest accuracy, but the results cannot meet the design spec. Solution number two is, hey, let's first fix the ASIC. Let's say we use a particular data flow, right? We use a weight stationary data flow. Now we design a hardware-aware NAS for that particular fixed ASIC. Now this way, the hardware is not optimized. So you can see that, yes, with the hardware-aware NAS, you can guarantee to meet the specs, which is the second row in the table. We can meet the latency, we can meet the energy efficiency, we can meet the area, all these constraints, but the performance in terms of accuracy is low. And finally, our framework provides the best trade-off between the accuracy and the hardware efficiency. It's the best. So this is the initial test we actually used in our paper. And then we actually also applied it for example, for our insertable cardiac monitor. And essentially, you can see that from the results, we get the highest F1, we get the highest accuracy, we get the highest model size compared with the state-of-the-art ICMs. As well as if we use some conventional backbone models with the conventional fixed hardware design. So we are the best. Unfortunately, in the interest of, there's something that's confidential here, so I can't really release too much detail on this. But essentially, this smart design outperforms any of the existing state-of-the-art ICMs. And following that work, we actually enhanced our framework to a lot of additional platforms. So for example, we extended to FPGA, That was published in DAC 19 and also the TCAT 20, which received the Best Paper Award. We extended to also consider quantization, and we extended to also for the network architecture. We extended to computing memory device, which not only includes the circuit level exploration, it also co-explores the emerging devices. And then we also extended to include the security and also the uncertainty aspects, which are especially important for medical devices, right? So we also extended that. And finally, we also did one more step forward, and we also did the co-exploration of quantum circuits and the neural architecture. That was actually done about 2 years ago. So this kind of like the whole spectrum of this along the works that were initially inspired by the on-device AI, the need of on-device AI for medical, for this kind of implantable and mobile medical device. We go beyond and also look at other platforms. Okay, so the next thing I want to briefly introduce is, like I said, so far everything we have done, they are mostly for the common good, right? The other thing I want to talk about is basically how do we make sure that we leave no one behind? How do we take care of the worst case, which is very, very important for healthcare applications. So the first technique I want to briefly talk about is the meta learning for personalization. So I think everyone's quite familiar with the personalization, right? So once I have a trained model that's good on the entire data set, before I would put it into each individual patient, for example, for this VA detection in the ImplantableCardioverter Defibrillator, I can just basically fine tune the data on that particular patient's rhythm, like the ECG signal. So you can see that on the figure on the lower right corner, you can see that actually the kind of blue ones are the ones before fine tuning, and the red ones are after fine tuning. So we do get a better performance after fine tuning for each patient. But the problem is that we find actually, if you actually allow the training to be done in different ways, as shown in the figure on the lower left corner, different ways, different models, different trainings would actually lead to different final personalization outcome. So our first question here that we want to look at is, how do we better train the network so that it provides a better way for towards the better personalization at the end, down the stream, right? And so our idea is that, hey, we find that if we do a meta learning, this is the high level view of the meta learning, where we would partition the support data and the query data based on the individual patients. So we don't mix the data together. If you just partition your support set and the query set based on the patient IDs, make sure that the data of the same patient belong to the same kind of set. If that's the way you do the partition, and if you apply the meta learning technique to train the model, and I will skip these kind of data, but this is again just a standard meta learning with just the way to split the data. And if you want to know the detail, that was published in TCAT last year, so you can take a look at all the implementation details. But the idea is that, hey, if we do that kind of, we do a task batch, and then we, once you train this model with the meta learning, and then once you do the personalization by the fine tuning on each individual patient's data, it actually gets you a much better performance, as you can see here. So here we are showing that the different personalization results from the different techniques of the training of personalization. And as you can see, the rightmost one for each patient is the fine-tuning or personalizing result from our framework. And it's almost flat, the accuracy, close to 100%, much better than the other method, especially for patient 205 and for patient 335. We can basically eliminate the disparity in this situation. And let me just give you, right, these are all research. So we actually did the actual clinical trial, all right? So the figure in the center upper row is basically the actual design. It's an ICD, and we did the clinical trial. And I can show you a small video showing our clinical trial done last year. So if you look at the monitor, basically, the second row, the first row is showing the ECG signal. And you can see that we are using the 50 Hertz alternating current to induce defibrillation, right? That life-threatening situation. So you can see that with this alternating current of 50 Hertz, the patient would, we would be able to induce the event. So you can see on the, it's no longer like the regular heartbeat, right? You are seeing this irregular patterns. And once this is being induced, the ICD design will be automatically be able to capture this event in real time, and then it will deliver shock. So you can see towards the end, if now you look at the screen, the normal heartbeat, the rhythm has been restored after the shock. So it was a pretty successful trial showing that our solutions actually can in fact be successful in real situation, in real condition in the clinical trials. And so that's one solution. Now let me spend the rest, maybe the remaining 5 minutes or so, talking about another work I think is quite interesting. So let's step away from the ICD, from those kind of cardiac kind of design, right? Because again, implantable and mobile device, they're not just all about cardiac healthcare. So let's think about in general, or maybe like a mobile healthcare, right? If we want to put a mobile device, like a neural network in a mobile device, and we know that when we put those kind of big neural networks in a smartphone, there is always a size or memory or those kind of energy constraint where we have to do the pruning, right? So here's I think everyone here familiar with neural networks know that pruning is a very old, very standard technique. You just basically throw away some of the neurons, throw away some of the weights. That's a very old technology, right? But our question here is, can pruning help to address the fairness issues? All right, can we do pruning to make the model more fair? Or an underlying question for this is, are all the weights created equal when we talk about their contribution to disparity? Or would there be some like hot spots in these kind of weights that would actually lead to that would actually contribute much to the final disparity? So to answer that question, we look at the other parameters. So let's say that the E is our loss function. And we can do a Taylor expansion of the objective function or the loss function with respect to theta is the weight. So there are two different situations. One, if you prune it, the weight is 0. If you don't prune it, the weight is whatever the weight is, right? You can do a first order, you can do a second order Taylor expansion as shown in the equation here. Now, the 0th order is a constant, which would cancel each other after you do the, so we don't care. The first order term, if you do a gradient descent based method and you train it all the way to convergence, the first order derivative would be 0, right? That's a gradient descent. So that term disappears. The second order terms would consider the diagonal terms and the off diagonal terms. Theta I, theta j would be the off diagonal in that Hessian matrix. And usually there's a theorem behind saying that those off diagonal terms in the Hessian matrix, under normal conditions, they are typically much smaller than the diagonal terms. So we can also ignore those off diagonal cross terms, which would only leave the second order diagonal terms for each weight, right? And that is what we call the saliency. The saliency is it's basically a reflection of how much perturbation on the model's final accuracy or the final loss function you would have if you change a particular weight when the model has optimized. All right, and if we ignore the high order terms. So then the main or the high level idea would be, right, maybe we just look at the saliency of each weight with respect to each class of my input, each class of sensitive attribute. In this particular example, right, let's say I have for the skin disease diagnosis, I have a light skin color attribute, I have a dark skin color attribute. each would, all the images from the light skin color would give me a loss function. All the skin colors from all the images with the dark skin color will give me a second loss function. And then I can evaluate for each weight. I can look at its saliency on these two loss functions and see what's the difference. Now, if the saliency in these two different loss functions are very close, that means that weight would contribute equally to these two loss functions from the data set of the light and data set of the dark. So that's probably okay. If we do have a weight that contributes a lot, well, to the difference of these two. So it basically means that the weight would lead to a big value between the difference of these two objective functions in terms of saliency. That weight is actually problematic. Then the question would be, do we really have some weights that would lead to big difference in terms of saliency on these two loss functions? And we plotted for all the weights here, we plotted like along the x-axis is the parameter index for each weight. We do a hot map. So basically, the lighter the color is, the bigger the value is. So you can see that if you zoom in on some area, you can see that in fact, there are some weights that contribute very little to the first, to the images with the light color, like the loss function from that part of the data, and they contribute a lot to the image that come from the dark color, in the loss function. So these are the weights that we believe are problematic. They would create this kind of unfair situations. And the idea would then be, hey, maybe let's just prune them, right? In addition to only look at the accuracy, the magnitude of the weights, when we decide which weights to prune, perhaps we are also looking at this difference. We call it importance score, which is the difference between the saliency on this across different sensitive attributes in the loss function across the different sensitive attributes, right? So I listed the detailed pruning recipe here. If you are interested, you can look at our paper that was published in Mikai last year. And by the way, this paper received the highest rating across all the reviewers and the area chairs. And so it's ranked #1, basically by all the reviewers. We actually show that there are weights that contribute to fairness. And we believe that, and we show that if you prune these weights, you're going to get much better fairness. And our results, again, we worked on the fairness kind of problem in the skin disease data sets. We look at two different data sets. One's from Fitzpatrick, one's from ISIC. These are both data sets that are available in the public domain. The first one, we used the skin tone as the sensitive attribute. We wanted to promote fairness across different skin tones. The second one is basically we use the gender as the sensitive attribute. So we find out actually that if you do a vanilla training, you'll find out that the female actually benefit. So the existing skin disease diagnosis models actually give higher accuracy for females. And so we actually used a few commonly used fairness metrics used by the community. In this fairness community, one would be the equalized opportunity, EOP. One is the equalized odds. Without going into too much technical details, basically these metrics evaluate the difference in terms of true negative rate, false negative rate, true positive rate, false positive rate across different sensitive attributes. All right, so that's these metrics. And here are the results on the Fitzpatrick data set. You can see that basically our model actually significantly improved the fairness in EOP 0, EOP 1, EOD, all these three metrics. We are much, much better than all the state-of-the-art methods in terms of fairness in enhancement. And we only have a very slight degradation in accuracy in terms of precision, recall, and F1 on the entire data set. And similar observations can be made for the ISIC. We actually achieved a significantly improved fairness across different genders, male and female. And we also have very slight degradation in terms of accuracy only. So in conclusion of my presentation, today I've shown that the mobile and implantable medicine, they are in fact playing an increasingly important role in healthcare, especially given the COVID-19, right? There's this big boost in terms of mobile medicine, mobile healthcare, telehealthcare in the past few years. So AI can significantly benefit the domain through the low-cost, automated, and precise intervention. And there is also we have to take into consideration the hardware resource and the model fairness, that these are the two biggest bottlenecks that need to be addressed. And in the talk today, I present some of our very initial attempts to address the problem through the hardware and neural architecture co-exploration, the meta-learning for personalization, and pruning for fairness. But there are still a long way to go. Further research is needed towards the AI democratization in this particular domain. And finally, I'd like to thank all my postdocs and PhD students. Without their really hardworking and support, all these works would not be possible at all. And also, I would acknowledge all our sponsors and collaborators from the different hospitals, from medical schools, from DOD, from NSF, from NIH. Most recently, we got a grant from NSF on this fuse teaming that would allow us to continue to explore in this particular domain, how to better do this kind of AI for on-device learning in this particular domain. And also, I'd like to show a very special thank you for my wife. Today is actually her birthday. So, again, she actually helped me a lot during my career. Without her, the work today would also not be possible at all. And finally, here is a list of all the works that we have published in the past few years. Just in case, most works here on this slide, they are for this co-exploration on different hardware platforms. And then we also have some additional publications along this, in general, AI for the healthcare domain, and especially the two papers that were published just this year in Nature Machine Intelligence. They are about the using the AI for ICD, and in general, we talk about how the challenges and opportunities for this particular domain in the last paper. So if you're interested, you can check out that paper. So I think that's everything for my talk today, and I'd be happy to take any questions you might have. Thank you.
Thanks, Yihu. It's a fantastic work, very productive. I also personally very impressed by not only applied AI machine learning methodologies into the medical applications, but also bring back and concrete the foundations of the AI and computer system development. It's fantastic. Thank you so much, and for the wonderful work and the presentation, and thanks and happy birthdays to your wife as well. So there are some questions, and the first question from Ashwin Bhatt. What is your opinion on the interpretability of this model utilized for safety critical tasks?
Okay, that's a great question. So in fact, I was chatting with someone a few days ago on this. There was actually a general consensus, or maybe conclusion in the community from the AI model security domain, is that there is actually there is always a trade-off between the model explainability and the model security. In other words, if you want to enhance the model explainability, it's always very likely that you are sacrificing the model security. And at the same time, for this particular domain, it's equally important to have a model explainability and the model security. So I think that's another big area where a lot of research can be done, right? So for example, right, we are predicting, again, taking that implantable cardioverter defibrillator as an example, you want to monitor and identify, hey, this isn't a VF episode. It's very, very dangerous. Now, why do you think it's a VF episode, right? In the current ICD design, we use rule-based, so we exactly know which rule actually trigger this event. But if using the AI, what is the conclusion based on? It is very important, and we had some work that was done in this area. I think last year there were some papers, but I think this is still a big area that needs to be explored.
Next question is in FairPrune is amazing. Is it explainable in associating certain layers in deep neural networks to certain subtext and features?
That's a very good question. So that's something we are looking at the same time. We're actually now looking at, some of the students are looking at this problem. So we want to know, and we're also very curious why some of the neurons are actually contributing much more to the final disparity than others. What actually leads to these neurons to look at to actually create a problem, and what are the distributions? So we do not have an explainable. It's not really a kind of layer specific. So it's distributed. So we're still looking at it to see why we have these neurons that are creating problems. But yes, I think that's an interesting question.
Now we're trying to understand neural network and how is it working. One follow-up question related is, does the FairPrune approach support differential machine learning?
The model as it is now, it's not designed to support differential machine learning, but I think, yes, it'll be interesting to extend it to see how it works on differentiable machine learning techniques.
Seems people are really interested in this topic. Has FairPrune been tested with people with the disabilities or disfigured faces?
This is a very good thinking, a very good question. We have not, but we have an NIH grant on this, and we are working with the UPMC and also Professor Jintong Hu from University of Pittsburgh. We have an NIH R01 grant that actually tries to see how this would help to promote the fairness in the RPPG. Again, where we take a video of your face and then see what kind of blood pressure and what kind of heartbeat rate heart rate would be reflected. There are fairness issues in that as well, based on the face kind of attributes. And we are seeing that if our method can be extended to that problem, and so the doctors at UPMC are collecting the data for us. So that is hopefully I will be able to answer this question in the next year or two.
Okay, very interesting. There are also there are also some questions talking about and getting copied of the recorded presentation. Bailey is the right person to answer this, but in short, and we recorded and going to publish on the CETA website, and you are able to obtain this. Well, I guess there's one more question. Do you have a solution to IoT-based federated machine learning in the surgical room for monitoring patient physiological responses?
Physiological.
Physiological, yeah.
Yeah, that's a good question. I do not have a solution for that yet. We have done something along that line that was again published, I think, a couple of years ago in the surgical room, but not to monitor the physiological responses, but really to use the kind of the IoT-based machine learning to allow a remote we call it remote surgery or telesurgery, where experienced doctors in a remote area that would allow them to real-time guide the operation, the surgery through this telemonitoring of the surgery. I think that work was published in ACM Communications of the ACM in 2021. So if you're interested, you can check out that paper too. So we had some attempt, but not to the physiological response. No, not to that level yet.
I just feel this is very inspiring discussion. Unfortunately, we are about the time, so I'd like to thank Professor Yu Shi for the fantastic talk. And also, if you have any questions, and either say, hey, feel free to contact Professor Shi for discussion and collaboration. Thank you all again for participating today's and DL seminar as well. If you have any feedback, and please send that and Bailey and me know. Thank you.
Thank you, everyone. Bye-bye.